our esteemed speaker this evening has been working at Microsoft, get this, since 1997. By show of hands here, has anyone been at the same job now as they were in 1997? Anybody? Not a one. Okay, well, you got the longest tenure in the room at this point. He's currently partner engineering director at Microsoft, and he's also the founder of Azure database, Azure DocumentDB, way back in the year 2011. Please welcome Dharma Shukla.
Well, thank you all for coming. It's really satisfying to see a full house of database enthusiasts interested in tonight's topic. My name is Dharma Shukla. I run DocumentDB engineering at Microsoft. So I thought I'd divide this talk into three parts. I'll start with the history, the origins of the project, some of the trivia questions were based on that. Then I'll talk about the problems that we are after. These are the class of problems that DocumentDB tries to solve, and these are the problems that we are very interested in solving. And then I'll talk about, for the rest of the talk, which is a large majority of time we're going to spend on a set of key ideas that influence the design of the system. Now, these are the ideas. So instead of looking at every subsystem of the entire stack, we're going to look at the system using the lens of these ideas. And hopefully you'll find many of these things very familiar. So the history. In 2010, 11, so DocumentDB started out as a project to serve the needs of first-party or internal applications at Microsoft. These are large consumer applications which required a distributed database, a document-oriented database to meet their scale requirements. They also wanted this database system to be extremely cost-effective. So multi-tenancy is a core element of this system. More importantly, the need for these internal applications was that they wanted this database system to eliminate the impedance mismatch that exists between the applications and the database system. So they wanted rapid iteration, schema evolution, all of those features from the system without any friction. So back in 2010, 11, it started with yours truly, and we put together a group of people across Microsoft. Slowly, the word spread. Back in 2011, it was called Project Florence. Slowly, the word got out, and more applications found the use of the system. At some point, we threw away the prototype implementation and started, building the foundation brick by brick. Put together a team, and more and more teams inside Microsoft started using the system. At some point, some of them started going into production on top of DocumentDB. So in 2014, in August 2014, when we found that we felt that we were operationally mature, we released it in the preview mode to the external developers. And then just last month, on April 8, 2015, we announced the general availability of the service. So you can run your business. All the SLAs are now in effect. So that's the arc of this project. Now let me talk about the set of problems that these internal applications drove. So all of these problems that I'm about to describe have one thing in common. These are the problems for which the existing NoSQL storage systems or the existing databases, they offered sort of a binary choice. So as engineers, we thought, as a matter of principle, that there has to be some shades of gray or some click stops between these two extreme choices. And I'll talk about the problems and describe the binary choices, and you'll find them very familiar. So the question we asked was that, first of all, are these choices valid? And are there valid click stops along this spectrum of choices that provide better alternatives to developers. So the first is a very famous one. So you get, if you're a geo-distributed data store, you have strong consistency with high latency on one side. But if you forego consistency, you have eventually consistent system, you get low latency, better availability characteristics. Obviously, eventually consistent systems, in our experience at Microsoft and externally as well, they're very difficult to reason over how eventual is eventual, when do the writes converge, is it infinite upper bound or a predictable upper bound to get consistent reads. So these are very hard to reason over. On the other hand, strong consistency is also, it comes with a steep price. Along this spectrum of strong and eventual, therein lies a wide array of distributed systems consistency levels. So you have strict and linearizable and sequential and boundary stateless and consistent prefix and so on. On the strong side, on the eventual side, you have causal and weaker forms of consistency, session, read your writes, weaker forms of consistency. Interestingly, if you notice, there's also a red-blue consistency. So we asked this question: which of these? This is, as you can see, this is a wild west of consistency levels. Which ones among these, present clear trade-offs along the consistency performance spectrum? Which ones of these are programmable, easy to reason over, they're useful, and most importantly, if we expose these consistency levels, then can we provide assurances or any kind of SLAs around them? So the state of the world in this for this problem space is sort of like the world of relational databases before isolation levels were codified. So this is a wild west, and this is a problem we are very interested in solving, because this is a very practical problem, and internal applications at Microsoft felt the need to solve this. So DocumentDB, we explored a set of consistency levels along these spectrums, which meet all of these criteria in terms of programmability, in terms of providing assurances and usefulness. And we validated some of these with the first-party applications. And then we are on the path of exposing them progressively as and when we find the right ones, we exposing it to the external developers. The next one is also, this is also a very familiar one. You have, on one extreme, you have your schema first, your relational, you provide, you give your schema to database, design your schemas, provide secondary indices, and you get rich, relational or hierarchical, and transactionally consistent queries. On the other hand, you have the schema-free promise. You are a key value store where value is largely opaque. It's a blob. It could be JSON or XML or serialized .NET Java objects. But because the value is an opaque blob, it's very difficult to reason over by the database engine. So if the database engine asks you to provide secondary indices, which is the extra metadata that is required to index the value. But in this approach, the queries remain relatively poor. So again, we ask this question: is it possible to take, schema-free part? Are there data models that allow the database engine to index without worrying about, without requiring schemas or secondary indices from developers? And we found a set of data models that are very suitable and a set of algorithms that work on these data models, very suitable for query processing, for indexing, without requiring any help from the developers. So again, this is a problem that we are very interested in solving, and you will see along, during this talk, there are many examples of this that I'll hopefully demonstrate. The third problem is very famous as far as Martin Fowler and Hotworks and this building. You have objects and database schemas, and therein lies the Vietnam of computer science. You have OR mapping problem. You have programming language type system, database type system, split. And so once we settle down on a data model that allows us to do indexing in a sort of a schema agnostic manner, we look for, are there programming languages that support these data models natively? And if we settle on JSON, then JavaScript is sort of the JSON and JavaScript marriage is a marriage made in heaven. So can we execute JavaScript stored procedures, triggers, or any compute directly inside the database engine in a way that is deeply integrated. And I have some examples to show how we do that. So this is again this divide and how to find alternatives instead of these binary choices. This one is if you're using cloud, if you're hosting databases in the cloud, then you know about this problem. On one hand, you have great performance isolation, great resource isolation for your tenants. But it comes at a high cost because you have to host database instances in dedicated VMs or containers. On the other hand, you can pack a lot more tenants on a single machine, but you get this multi-tenant or noisy neighbor problem. You get very, very weak isolation as far as performance or any resource isolation is concerned. So we asked this question, are there ways, can we solve this problem by applying some techniques that will allow us to be as cheap as we possibly can? And this is a quest. There's no final destination for this, but can we operate the services as cheap as we possibly can, but still provide performance isolation and resource reservation guarantees? So DocumentDB, this is a problem we're interested in solving. Then this is related to the popularity of NoSQL storage systems. And one of the attractions of these systems is that you get, if you own the management of database systems as a developer, you can hack it. They are hackable. You can configure it depending on your workloads, depending on the access patterns, depending on your use cases. You can configure the system, every aspect of the system, including the database engine, the replication, and so on. But you own the management aspects of it. You carry the page. On the other hand, if it's fully managed, you lose control, the hackability. It's left to the hoster. So again, we look for ways in which are there ways of providing developer tunability of commonly used features so that developers can fine-tune the system for their different workloads without having them carry the pager. So fully managed offering without developers having to deal with any of the capacity planning, managing VMs, and so on, but still make it configurable. So these class of problems are in a nutshell the kind of problems DocumentDB tries to solve. And these are the problems as a team we are interested in solving. So in a nutshell, this is sort of like, what is it? This is what it is. It allows for rich SQL and JavaScript queries, which are transactionally consistent, or schema-free data models. And one of the popular data models is the data model of atom records and sequences. And it so happens that JSON is a most ubiquitous format that belongs to that particular data model. So we exploit that. It's a nice coincidence that data model on which we could do this, we could run these algorithms, JSON natively supports that. And since it supports it, and since it's a subset of JavaScript type system, we also exploit that fact and run JavaScript directly inside the database engine in a very deeply integrated way. I have some examples I'll show. This is the consistency point, and then it's fully managed. One other thing is that we expose the entire system using open protocols, using HTTP, REST, etc. So you can write SDKs or drivers on top of it relatively easily. So I have a 2-minute video. I'll start this video, and then we'll get into the key ideas and the design of the system.
Today, application development is accelerating and becoming more iterative as end user needs rapidly evolve, data sources diversify, and release cycles shorten. NoSQL has emerged as a complement and alternative to relational database systems to ease these development challenges. NoSQL solutions can be hard to set up, manage, and scale unless you have a team of qualified experts on hand to help. We're here to help. Microsoft Azure DocumentDB is the first NoSQL document database as a service that embraces industry standards like JSON and JavaScript, offers predictable performance, and grows to meet the needs of your application. Better yet, DocumentDB can execute queries using familiar SQL, all in one easy-to-use database service. DocumentDB is schema agnostic, which means you can revise application data models as needed, without dealing with complex object relational mapping frameworks or constantly rolling out upgrades to the data tier. All the data you store in DocumentDB is automatically indexed, so you can query anything at any time. DocumentDB also enables you to leverage existing JavaScript development skills to execute transactional application logic over multiple documents through JavaScript-based triggers, user-defined functions, and stored procedures. The best part? As a part of Azure, DocumentDB integrates with HD Insight, Azure Search, and other Azure solutions to simplify modern application development. Get started with Microsoft Azure DocumentDB today using your Azure subscription. And if you've yet to check out the benefits of Azure, try a free trial today.
All right. So let's look at the system, different parts of the stack, with the lens of these ideas that I mentioned. So this is the data model. This is the distributed data model of the system. At the very top, using Azure subscription, you create a database account. You can create one or more database accounts using your subscription. Under an account, you create one or more databases. And you can partition your databases in terms of collections. So you can add documents directly to database, and underneath the covers, you can partition it across collections. A collection can contain any arbitrary document, or stored procedures, triggers, user-defined functions. These are the things you associate with a collection. So under a database, create any number of collections. Under a collection, you can just dump documents without worrying about schemas or giving secondary indices. Under a database, you also can create users. Users, you can associate permissions. Permissions are these authorization boundaries or domains. They are like ACLs, using which you can give permissions, authorization, set authorization rules for different entities here. Few things to note. This is a distributed resource model, or the distributed data model. It spans machines, clusters, data centers. It is very logical in that you interact with them using logical URIs. Each of these entities that you see here they're scaled out using horizontal partitioning, but you get this hierarchical overlay on top. And the referential integrity of these entities, which are scaled out across machines or across clusters, is enforced on top. You interact with these entities using logical URIs. You don't worry about the failures of those machines or physical endpoints that are behind these logical URIs. Each of these entities are partitioned, and they are made highly available using replication. The way you interact with any of these entities, which we call resources, is using a very stateless protocol, using standard HTTP verbs. So it's RESTful interactions. You use standard HTTP verbs to write. There's also a TCP protocol, which is an efficient version of that, but it's also designed to be very stateless. The stateless protocol is very essential for resource governance and multi-tenancy aspects. I'll come talk about it later. But that's the reason why we chose stateless protocol. All of these entities are represented as JSON documents The ones that are, some are system controlled, like database account, database users, selections, etc. These have sort of fixed schemas or system-defined schemas. The rest, like documents or stored procedures and so on, they are just arbitrary JSON documents. If you want to scale out a database account, you scale a database account by creating collections. If you want to scale out a database, databases, the account is scaled out by databases. If you want to scale out a database, you create collections. So, in a nutshell, this is sort of the top level interface that, or the concepts and the top level interface to program the system. You interact with it RESTfully, logical URIs, hierarchical distributed resource model. Physically, in every Azure region, and we are in US East West right now, we are in Asia, we are in Europe, and soon we'll be in other parts. We're sort of following wherever is an Azure region, we get deployed. So DocumentDB in any data center in a region, we have dedicated stamps of machines. On a given stamp of machine, we create an overlay network, which is peer-to-peer network with a ring topology. And we first deploy a set of system services which ensure consistent routing of messages, reliable messaging, failure detector, group membership, things like that. And then on top of it, for every entity that you saw in the logical model here, each of these entities map to partitions, and each of these partitions were made highly available using replication. All of those entities, they get placed in those partitions on the machines. For every partition, there is a replica set that protects that partition. So there is a set of replicas that protect that partition. These replicas are spread out across a set of fault domains. And now, note that replicas belong to a partition, partitions are placed on a machine, and partitions correspond to those entities that we saw. Those entities scale out by partition. So effectively, every replica is associated with a tenant, or a user, or a Azure subscription. So on a given machine, we place as many replicas as we possibly can. This is to make it very cost effective. But we make sure that every replica lives within a fixed set of budget that is provisioned for it, and it provides performance isolation within that fixed set of resource budget that was allocated to it. So every tenant, every replica belongs to a tenant, and it operates within a fixed budget. A replica is a piece of code that implements the replicated state machine, and it hosts an instance of the database engine. And this database engine implements transactions, it does JavaScript runtime, it does indexing, it does a query processor, it has a B tree, all of that stuff. So far, makes sense? So this is the sort of the physical manifestation of the DocumentDB service in a data center in the region. Now let's explore. So I'm going to go through this like this, one by one, different parts of the stack. This is the sort of the overall picture of the stack. Remember, cluster, machines, replicas running in set of processes on a machine. Each replica belongs to a unique tenant, and each replica hosts an instance of database engine and implements a replicated state machine. So, with that background, let me go into multi-tenancy. So the idea here is that we want to have hundreds and hundreds of tenants on machines and clusters in a data center. So the tighter we pack, the more cost effective it becomes. But the tighter you pack, unless there is a strict resource isolation or performance isolation, you get this noisy neighbor in which one bully tenant can steal the system resources that were assigned for other tenants on the machine. So the typical observation is that you have very, very few large tenants. They are interspersed among lots and lots of small tenants. So it's very essential to provide this kind of performance isolation. Also, the performance isolation has to be, ensured in the face of different generations of hardware, because at any given point in time in a data center, we are dealing with multiple generations of hardware. And also in the face of different offers. So we have a premium offer, you reserve more throughput, a basic or low-end offer, which is less performance or lower performance guarantees. So all of these different types of workloads and different types of tenants are packed on a same machine. And so how to isolate them effectively? So you can have a model. There are models where you can have a tenant, then you create a small, you have a pool of machines, you carve out a subcluster, and just assign the entire subcluster to a tenant. This is obviously, it's very costly. Then you can have a model where one tenant is mapped to a single machine. It has all the resources of the machine. Here, this is very lavish. You have a bunch of machines assigned to this, but it's operationally very painful because as a service, you have to manage so many different clusters. One, it sort of linearly grows with the number of tenants you have. This model is relatively better, but it's associating one tenant to a machine. Then you can go further. You can associate multiple tenants to a single machine. In this particular model, the assumption is that all of these tenants belong to one specific offer, or they run one specific kind of workload. And the model that we use is the model where you have heterogeneous tenants. They belong to different offer types, and they run different types of workloads, and we pack them together, and we assign them to a single machine. So one single machine hosts diverse set of tenants. So in order to do that, the mechanism of doing that is through resource governance. So when we build the stack, the entire stack, all the components of the stack have resource governance built in from the ground up. So you can think of the entire DocumentDB stack as a set of feedback control loops with back pressure and rate limiting sort of ingrained. The first thing we do is that to a customer, to a tenant, we define this logical currency. Think of it as a Bitcoin. It's a rate-based currency. This unit, called request unit, it includes a slice of memory, a slice of IOPS, a slice of CPU. And this is a logical currency. And every replica which belongs to a given tenant is associated with a bunch of these request units. You say every replica has to live within the budget of these units that are assigned to it. And when you issue requests against these replicas, if you issue a get of, if you read a document of 1 kilobyte size, then you consume one request unit. If you do an insert of a document of certain size, you consume 2 request units, and so on. So every operation that you issue against the system, you consume some request units. So the offers that we tailor are in terms of these request units. So if you have, this is one of many possible offers, and this is one of the current offers that we expose. We have S1 offer, which gives 250 request units per second for some price. We have S2 offer, which gives you 1,000 request units per second for some price. We have S3, 2,500 request units per second for some price. So at a given point in time on a given machine, there may be replicas belonging to any of these different offers. And you can change this. So on a collection, you can set the collection's offer as S1, which is 250 request units per second, which is when the traffic is low, I would set the offer type as S1. And when the load increases, I will change it to S3. And so I get more performance out of that collection. better throughput for that tenant. So the distribution of you can, since all the tenants can change these provision different offers and different throughput, the distribution of these offers on a given machine will keep changing over time. And so the replicas you keep changing how many request units we associate with each of these replicas over time. So let's say if you purchased an S3 offer with 2,500 request units per second, and you start the caller started making requests which are more than 2,500 requests per second, then we will rate limit the caller. It's a progressive rate limiting mechanism. So the harder the requests come, the farther in time they are sent. So if you come with 3,000 request units per second, you're sent in future. If you come with 5,000, you're sent farther in future. If the requests come in at a lower rate than 2,500, then we serve them. That's a part of the predictable performance guarantee. If they come in very low for a period of time, for that second, if the request volume drops on that replica below a certain threshold, then we use whatever spare capacity of resources which were budgeted for that replica. We use that for doing background tasks like running garbage collector for the log structure store, or enforcing building views, or doing some other cleanup activities which are background activities on behalf of that tenant's replica. So that's the model.
The composition of the request unit, right? Say it consists of memory, CPU, and IO ops. So some workloads may be CPU intensive and some may be memory intensive. So that also can be configurable. Okay, in one unit I want this much of CPU, this much of.
The way that the system is designed, the interaction model is designed such that you purchase these request units, and we assign, we map these RUs to the physical resources, depending on the kind of operations you do. So if you're running a stored procedure, which is JavaScript, and that's doing some compute, then we will consume CPU, the request units CPU. If you're issuing a lot of I/O, then that. But the key thing to note here, remember we talked about the stateless protocol. So all requests that you made to the system, they terminate in a fixed amount of time. So in 5 seconds, all requests terminate. So you can consume 5 seconds worth of request units in the worst possible case, right? So if you were to do computation which is longer than those 5 seconds, then you come back with a continuation token. This allows us to scale far better than a stateful protocol where a bunch of tenants just park the request and then do some long-lived work. And in many occasions, that work is sort of thrown away later. And that's waste of resources. Make sense? So this is one of the ideas. The other thing that we talked about was consistency level. Like I mentioned, we're very interested in exploring this between these two extreme choices, the spectrum of consistency levels. So the system is geo-distributed by design. Currently we provide 4 consistency levels: strong, bounded staleness, session, and eventual. And we give predictable performance with each of these consistency levels. The way you configure the system is that when you create a database account, you get to choose your default consistency level, and you can beacon the consistency level on a per request basis. So you start with strong, you configure the account with strong, and you can beacon it over time on a per request basis. You also specify, this is not in the currently we don't expose this, but this is the design. You can also specify preferred write region and one or more preferred read regions. So effectively by specifying default consistency level, a read region and a write region, that allows us to place replicas which are in the read and write region and set up quorums suitable for a given consistency level that you configure. They are optimized for that consistency level. Quickly, bounded staleness is defined as you're willing to tolerate reads which are staler by X prefixes, or some number of operations. I'm willing to read stale data by lagging behind. So reads are lagging behind writes by some number of operations, by 5, 10, 100 operations, or by some interval, 5 seconds or 10 seconds, and so on. Session is one of the most popular consistency levels, and session ensures monotonic reads, writes, and read your writes. So session is this is the distribution that I had last night in one of the clusters. By a vast majority of customers are currently using session as the consistency level. And the idea here is that it gives as high, as close to availability characteristics as eventually consistent system. It gives very low latency, high throughput, almost like the eventual consistent system. It's a very useful consistency level, because most apps that we observe are, most apps, you interact with the system in the context of a given user. So once we have the session of the user, smuggled in the cookie, then we can find the right replica such that the user can always see his own writes. He can read his writes or her writes and sees monotonic reads and writes. We don't have to ensure global total order for that user, but the user is living in that illusion that he can see his writes and the world is consistent for him. So it's very popular for single user, single session apps. Bounded staleness is also very popular, and so these are the kind of problems we are after. We're interested in finding these choices along the spectrum, and we have also identified a couple of other consistency levels. We're sort of trying it out with internal applications and seeing, validating if they're really useful, and can we give any assurances, and how predictable can we make them. And once we're convinced, then we expose that to the external. Now I'm going to spend a lot of time in the next segment in this idea. This is a very interesting idea. This is the idea that how can we be schema agnostic, and we use this particular idea in a variety of features that I'm going to describe. So the idea is that there is a data model which JSON also belongs to. Is atom, records, and sequences. So a bunch of primitive atoms, and then records, structs, and then sequences, arrays. So if you have a data model like that, and if you represent an instance of that data model, which is this document here, this document can be turned into a tree. We insert a fake root at the top, and every array that you see here, the locations is an array, has 2 elements in it. Every array that you see exports it in the same way. We add a node in the tree corresponding to it. Every label in the document it maps to a node in the tree. So you can take any instance of this data model and turn it into a tree. And then the rest of the system, the database engine, the runtime instantiation of variables, everything that we do, and I'll walk through different examples of this, operate on these trees. So it has a number of side effects, good side effects. We can do automatic indexing of documents without asking for schemas. The SQL dialect for query that we have, and the JavaScript query language that we have, they all exploit this notion of trees. And I have some examples we'll walk through. And even the instantiation of variables in the JavaScript runtime exploits the fact that the values in the runtime, they map to these trees. So a lot of nice side effect of this one idea. So this is how we exploit this idea. Consider these 2 documents, document 1 and 2, each represented as tree. And so the index is, conceptually, the index is just a logical union of all of these documents, so all of these trees. And a bunch of interesting observations. So if you union all the trees in a large corpus of documents, you'll find that there's a lot of common structure which is in the interior nodes. So one of the sweet side effects of representing these this data model, instance of the data model as a tree, is that the values, which is Germany, France, Berlin, Paris, Moscow, Belgium, these are usually located on the leaves, and the structure of the schema is in the interior nodes. And we exploit this fact. So when we see the index, all the documents logically just union of all these documents form an index. When you have an index like that, you'll see that every node in the tree also has a back pointer to all the document IDs that contributed to that node. So if there is a node like location which exists in multiple documents, it just keeps one instance of it and points to all the document IDs that contain that label. So the usual variation or the variance is isolated usually, mostly, to the leaves. Sometimes interior nodes contribute, but largely it's in practice, it's isolated to the leaves. Then what we do is that we create paths from the root to the leaves, sometimes from the leaves to the root, and sometimes transformations of these paths from either root to the leaf or leaf to the root. So for example, range queries are served with a certain path orientation. Wildcard queries are served with certain other path orientation. Spatial queries, where we take a segment of GeoJSON, transform it using a variety of transforms, map a point on the curve, and then hash that and point it as one of these paths. All of these path segments, they overlap, and all of these path segments form the keys in a key value store. So the index is term and postings corresponding to that term. So the path that we find there are different ways in which we generate paths, but each of these paths were paths in this large index tree. The index tree was formed by unioning all of the documents, which were themselves represented as trees. And then the postings correspond to what were the document IDs that contributed to that particular path. In practice, this is a graph that shows, in practice, we see the distribution is that this is the standard, the graph that you see where the practical distribution is such that there are many terms which have document frequency of 1. So these are usually the unique terms located on the leaves. And then there are terms with large concentration, fewer terms with a large concentration of document IDs. So the idea for, so just to recap, representing instances of the data model, JSON is a good example of that. In terms of trees, index is represented as unioning all of those trees, observing the fact that the values are largely concentrated in the leaves. The interior nodes contribute the schema or the structure, and then using paths and commonality of paths across the index tree to automatically index the incoming documents that are coming. And then representing the index on the secondary storage, or the logical index is represented as an inverted index. The trick here is to make sure that if you're doing this, to make sure that the upper bound of the index overhead remains, in a fixed. There's a fixed upper bound to the index overhead, and so the postings are dynamically encoded using various encoding schemes are applied. The keys are encoded dynamically. There's a model like the memory hierarchy where we only use every byte counts, so we only use bytes that are required depending on the size of the corpus, the size of the index. And there's a lot of work in terms of the maintaining the on-disk upper bound, in terms of the budget that is given to the log structure storage, the budget given for garbage collector to run, and so on. But this is the idea that representing documents as trees enables this schema-agnostic indexing. The other example where the same idea is exploited is in queries. So notice this is a simple query. These are the two documents, but there's an interesting thing about these documents. These two documents, the second document has two extra properties, revenue and dealers, which are missing in the first document. And assume for a second that these are the two documents in a collection. And we find that the collection, the company that is represented by this collection, the headquarters Belgium, the document of the headquarters Belgium is found. This is the first document that matches that. So we're going to project out the locations array as the result. And when we do that, even that the output that we emitted, the result that came out of the query processing, is also represented as a tree. And so if you have recursive queries or nested queries, you can just take the output of one query, feed it as a tree to the next query, and so on. Another thing I want to point out on this slide is that the SQL dialect and the JavaScript dialect, their type systems are rooted in JavaScript. So this is the _JS version of the same query. And again, it also works the same way over the trees, and its type system is obviously JavaScript. This is an example, another example where a user-defined function written in JavaScript is invoked from the SQL query. Because the type system of SQL dialect here is also JavaScript, is very natural and seamless to execute user-defined functions from the SQL. So here we're trying to find a document whose location.revenue. We're iterating over all the locations in the location array and finding any document that has a location.revenue greater than 100, and we find the second document that matches it. So we know it's the second document. And now we are going to project out location.city that's selected. And we're also going to calculate a text by invoking the text by invoking a user-defined function, UDF, called German text, which is written entirely in JavaScript, and to which we pass the revenue, which is 200. And the function is written in a manner that, if the argument that is passed to it is less than 1,000, then multiply that argument with 0.1. So 20 is the tax. So we are generating a new property called tax. We emitted it as a part of this result set, and then represented as a tree. So this is the same idea that we use the idea of trees as a way to process queries, trees as a way to automatically index documents without asking for schema and so on. Let me quickly, in the interest of time, let me quickly go through a different idea. It's related to this, but slightly different. So the basic model for reads and writes. So when a document is ingested, its document is received on a primary replica. We write it, we replicate it, and we analyze the document. When we analyze the document, we are going to generate these paths. Those paths that I mentioned, those are the paths in the trees of that document. And every time we emit out a path, we say, this is a particular path. We analyze the document, generate a path, and we say, is the document plus or minus? So some path getting added to the document, some path getting removed from the document if we replaced an existing document with another version of the document. So these pluses and minuses of the document IDs are documents that are from which the paths are being added or being removed. And these pluses and minuses commute. So when we do the writes eventually on the secondary storage, we exploit the fact that these pluses and minuses of the postings, of document IDs, they commute, and so we can avoid read IOs in order to do this writes of the postings. And I have some slides to talk about those later. But then we eventually update the index. So the output of document analysis is we get a bunch of paths, terms and postings, and we update the index. And when a query comes, the query engine looks up the index, identifies the documents, and then performs the query processing of those documents and returns the results. So this is the main idea. So one of the problems with this model is that those paths that you saw, these paths, they have very little term locality. So when they are spread out on the disk, they can be on different pages on disk. So if you see here, these are the paths. Some term got added, others got deleted, some got inserted, updated. All of these paths, they will be on different pages on disk, and it's very difficult to keep in the hot set caching memory. So the idea here is that how can we avoid when we have to update the postings of a given term, how can we avoid reading a read IO to read the postings in order to update the postings for a given term. And since this terms are scattered across many pages, potentially it could lead to burning many IOs. So how to do this efficiently? So this is another problem, and in order to solve the problem, we are looking for a data structure that allow us. So all of these ideas, taking documents, representing them as trees, frees us from the schema, and allows us to do queries on the trees and so on. But then when it comes to writing them on the secondary storage, we have to worry about another set of constraints. So these are the set of constraints that we're looking for a data structure that can solve these problems. So first, it has to support high degree of concurrency, so we cannot acquire locks. It has to have really low read and write amplification. We need to support large sustained volume of writes, so we can ingest lots of documents. Remember, the offers were tailored around request units per second. So it will be more compelling an offer if we can take more amount of writes and index all of the documents without bothering the developer to specify schemas and such. So ingesting documents, doing synchronous indexing of all those documents, and knowing that there is no little term locality across documents that are being ingested. And to do this synchronously such that we can serve queries consistently. So if a query comes for a document which is about to be indexed, we can serve consistent results. And this entire thing has to be done in a very frugal, restricted budgets. So it's not that the entire replica has access to all of the system resources on that machine. As we saw earlier, all the replicas are packed, belonging to many tenants on the same machine. So for a while in the early days of this project, we tried different storage engines, tried different data structures, and eventually, after many years of partnership with Microsoft Research, we improvised on a data structure called BW tree, and we tuned it to be hosted inside DocumentDB's database engine. So this is, I have some pointers to papers, by the way, for many of these ideas. These are not ideas we take credit for. There are many ideas during this talk that I mentioned. I have papers, I can point you to those if you're interested. Just ping me after the talk. So this data structure is highly concurrent, it's latch-free, and it's copy and write, compare and swap based delta updates. It's log structured. It can take large, elastic sequential writes. And we devised this access method called blind incremental update, which is semantic update. which addresses this problem of how do you do merges or postings without incurring read IO while you're doing writes. And this has to be done in the face of sustained document ingestion. So I won't go in detail on this data structure for this talk, but if you're interested, just ping me, or after the talk, we can go in detail. Last couple of slides. So query processing pipeline is devised in a manner that both SQL and JavaScript both get compiled down to a set of opcodes. We call this query IL. Query IL gets compiled into a set of instructions. This IL is rooted in JavaScript type system. And so the idea here is to support multiple query front ends and leave the entire query processing pipeline, make it agnostic of specific front ends. So SQL and JavaScript dialect map to IL gets executed, and the type system of IL is JavaScript. So we have a virtual machine that can process IL, and we thereby sort of decouple the rest of the system from the query language that we expose to developers. Similar JavaScript integration, a quick slide. This is an example of how JavaScript runtime is integrated in the database engine. It's an example of a stored procedure. User submits the stored procedure. First thing, it takes two arguments, player 1, player 2. We issue a query. We filter for any document that matches one of the two player IDs. And if they match, we find the results. We swap the player 1 with player 2. We swap the two documents. And if the replace of the first document succeeds, then replace the second document. And if any one of them fail, then just throw a JavaScript exception. So the entire stored procedure runs in a transaction under snapshot isolation. And these operations are enqueued. There'll be, upon successful commit, there'll be, we'll run a 2PC across all the replicas within the replica set and commit this transaction. Or if they run into a throw statement, then we'll abort the whole thing. In this, places like this where a variable, var player 1 is declared. So this, the database, the JavaScript runtime has visibility into, the rest of the database engine primitives. So if var player 1 points to a massive document, then we will lazily bring it from the buffer pool. This is a direct pointer to the memory in the buffer pool. The transactional aspects are also directly mapped. Accessing properties is also made visible to the host of the language runtime. And this entire thing executes in a very constrained resources, or under very resource constrained execution. So that's it. More information, you can reach me on Twitter. If you're hiring, there's a link to DocumentDB in 2 minutes. You can play with the playground. There's a link. There are drivers and SDKs you can play. And there are some papers. I added links to some of the papers here. If you're interested in others, any of the other topics, please ping me or meet me after the talk. Thank you. Before
we go on to Q&A, I just want to remind everybody we are giving away some hoodies, Microsoft branded hoodies, Microsoft branded raincoats. I guess we'll give away 1, 2 now. The basket to put your card in is right there on the table. Can someone just add that pass forward, and we'll give away 1 or 2 now, and then we'll take Q&A. Thank you very much. Okay, let's see. Can I ask you to just mix it up? Oh. Pass that around. All right. Just look the other way, reach in, grab one out. This is for a hoodie, by the way. Luxury Patra. Alright, we're going to give away a jacket and then we'll go on to Q&A. Let's try. Have a card. Read it out. This is for a jacket. All right. You got a jacket? Let's go Q&A.
Last name.
Raise your hand. Alright, we're gonna get let me pass that basket around for whoever didn't get a chance, and we'll give away a mouse and a whole bunch of other stuff. Let's take the first question. Yes.
I have a question about replication between, I guess, Azure data centers. Whether we want to replicate write-only or rewrite other data centers. It's my understanding with Azure DB right now.
Is DocumentDB.
I'm sorry, yeah, DocumentDB. It's only within one Azure data center.
Yes. So this the picture that I presented, the design I presented, is the internal implementation. Currently, we expose a single read and write region. They are just combined,
Right.
and offer consistency levels as the only dial that you can control.
Okay.
You don't get to control the read and write regions yet.
Okay.
But the future offers that we will expose will let you specify this.
And that's something that's in preview externally, or just something you're
Internally.
Okay.
But we will explore it. But this is the design. The intent for me is to talk about the design pure without a specific point in time. But yes, we'll explore the models.
And then I just have one more follow-up, or one more question. Do you know if there's any plan for BizTalk services to be able to send data into DocumentDB?
Adam, do you know?
I don't think there's anything
I can
right
follow
now,
up.
but
I can
it's a
follow
good
up.
question. Yeah, I can find out for you.
Yeah.
Okay.
Thanks for
Bring us one building forward.
Okay.
I'm just wondering, like, is DocumentDB available without Azure as a, like, just to play around?
It's one of the most popular asks to make it. It's on the forums and everywhere else. Since preview, it's the most number one feature request, and we're actively considering it.
Oh.
But right now, you can just you get a URL, sign up for a free offer, and play with it.
Oh.
Well, that's it.
I mean, this is a bit like sort of, like apples and oranges, but MongoDB is obviously the big, 16-ton gorilla out there. Probably some customers who might be looking to work with DocumentDB, they already have some MongoDB databases out there. Do you have any type of integration or any type of support for integrating with Mongo?
Fantastic question. We have importers, data importers. So, from Mongo, from other data stores, you can play. There's on the SDK link. You can download one of these importer tools and import data from other data stores to document. Mongo is one of them. Reporting is not built in, but we are going to integrate with the rest of the data assets into BI toolchain. And so,
Thank you very much for the presentation. My question is there a way how healthcare solutions could be deployed using DocumentDB to keep a compliance, the sign?
So compliance, we are working as an Azure service, which is generally available. It has to be compliant, and there's a wide array of compliance checklists. We are working through different compliance standards. So this is on the roadmap. If you check out the updates, we'll keep posting as and when we support the standard.
In your presentation, I saw triggers in there. Is
Yes.
that for automated workflows? And if yes, how does it work?
So you can associate pre and post triggers with inserts, updates, deletes, and they will transactionally execute with the main operation. So you can have some pre-triggers, post-triggers. You can register the triggers with a collection, and then associate the trigger with the operation.
Alright, so there is not like multiplication service that you can post something to a service and then you go and do something with the document.
No.
Alright,
But these are traditional database.
yes.
So, I currently use MongoDB for a bunch of different things. I'm not a big fan at all, and we're looking at ways to get off of it, right? And I'm considering something like MarkLogic, which is definitely more expensive, but with a lot more functionality. Could you talk to me a little bit about, what benefits I would have with DocumentDB over MongoDB, maybe some features that I might not have access to with MongoDB, or some of the pain points? Like, I've got a lot of them with Mongo, but I'm curious as, this being a big
Safe by
competitor for you
default.
guys. Yeah.
Or start with safe by default.
I'm sorry?
Safe by default.
Safe by default.
It's reliable. The entire system is designed with an intent to solve a set of these problems that I described as a talk earlier. So there's a sound model for reasoning over consistency levels. There's a sound model for indexing, query processing. This is truly schema agnostic indexing. You can configure, you can have indexing policies that if you're an advanced user, you can say, I don't want certain paths or certain properties to be indexed, or certain documents to be indexed. But the system is sort of agnostic to specific schema, does not require secondary indices. So as your app evolves, there are not too many limitations like that, which you run with other data stores. In general, you should give it a try.
Well, that costs me, yeah, it's time and
it's
money to do that. So I'm curious what you think.
There are many features where, so this is, I would say, it's document-oriented database, so you compare it with other document-oriented databases, but there are some fundamental differences in the way the system is designed. This is multi-tenant. The scale model is very different. As you see, for example, MSN, 400 million users, and those class of applications taking dependency on this. It's deployed at a different scale, and these capabilities that I mentioned for indexing, query, running language integrated transactions in terms of JavaScript natively integrated inside the database engine, distributed consistency levels. These capabilities are sort of differentiated. Also, it's fully managed. So if your application scales out, your needs grow, you can scale throughput and storage independently. You run it as a fully managed service. You don't have to worry about capacity and provisioning machines and deploying data infrastructure. So these are the differences.
Thank you very much.
Are you executing all of this engine side on single machine, or that works on cluster as well?
What part?
When
So
you
so
have
yeah,
to, you
yeah.
have
So
to document,
so
is
this
it on single machine, or it can be held on the cluster?
so these the JavaScript execution happens on a given machine, not on a single machine. But the stored procedure, side effects of that the execution of stored procedure, they get replicated across replicas that are running on multiple machines.
Replicas I understand, but let's say your database is such a size that it does not.
Yeah, so database is a logical entity, right? It spans the machines.
Okay, so then how do you provide?
But the collections and those operations that are bound to a collection, they execute on a single machine.
I understand. How do you provide the transactional integrity if you execute for your, let's say, SQL statement
So
you
that,
execute on multiple machines? How do they do the transaction?
so the compute, the stored procedures where you execute a bunch of operated transactionally across a bunch of documents, that executes on a single machine because the collection is mapped to a single machine.
So you never use data locality. You need to move all this data from all the machine across the, your universe back to one machine and execute it there because it's one machine.
No. You have your data partitioned across many machines, and the partitions are called collections. And so when you execute a stored procedure, the stored procedure is executing for that given partition. So only it is operating across documents on that partition. Make sense? The database itself is a logical entity that spans all of those collections. Each collection is mapped to exactly one machine.
So you don't have the collection that spans across machines.
That's right. The thing of collection here is not as the collection in other databases. Think of collection as a partition.
That's very limited.
It depends.
No, I understand. It solves certain
Yes.
problems,
Yes.
but it's very limited. If you go to bigger data, I mean, it's
Then
So you partition your data across those collections. At the end of the day, you store data. You scale out by partitioning across machines. But the unit of transactionality for a stored procedure, so the transaction can span many documents, which are mapped onto that machine.
okay. I don't want to.
If you have like shards, as they call it in other products, the shards are different collections.
That's right.
So you have your parallelism.
Yes. So you can use we just launched a sharding SDK, using which you just add documents to the database, and it will manage the partitioning logic underneath it for you. So it will create collections. If the collection is saturated, it will spill over, create more collections, and so on.
We have time for just a couple more questions, but he will be here for one-on-one questions afterwards. Either one.
So, what is the limitation of the index? How many indexes you can have?
No limit.
What is the limitation for a document?
The document is 512 KB right now. We keep changing these limits. So once we validated with different workloads internally, we keep changing these limits. So right now it's 512. Future will go in more depending on the needs.
So let's say my application is write intensive, right? Is Azure DocumentDB is the right thing, or like it's a wrong setup?
We believe that we work really hard to make it right optimized.
Okay.
And so we believe it's a right.
So let's say I put the read of it. I just want to read in milliseconds, right?
Yes, so we do sub-millisecond read latencies.
Do you have any documentation on like how much it supports?
Yes.
And last question.
Wait, hold on. We got to limit questions because we're running out of time, but he'll be here for one-on-one questions afterwards.
I saw some kind of drawings you mentioned. It's there in one of the. Is it possible to do it while between one? No. It's within the documents assigned. So don't think of collections or these partitions as tables. Think of them as a bunch of heterogeneous documents belonging to any arbitrary schema just dumped on a machine. And now you're joining across the relations, across these documents, then they are not tables.
Within link, right?
Yes, you can.
Yes.
Yes.
Do we have time for one last question? Yes. Hands. Okay, everyone had their hand up. You got it.
I have a question about, it seems that you support a pretty rich query language, and you also, the way you charge or the way you provision is for units of computation. As a developer, how can I know if this is a query, how much is going to take, or
We
how much
return the
is
response error, we tell you the charge.
Dharma Shukla will be here for one-on-one questions. Thank you very much for coming. Thank you, Dharma. We're giving away some free gifts. this is for the mouse. Manu? No Manu. Okay. Reach in, grab another one for the mouse. Read it out.
Vikas.
All right. Vikas, you got yourself an ArcTouch Microsoft mouse. We have. And then here's your mouse. Reach in, and this is for a Marma jacket. Read it out. James? Nobody. Reach in and grab another one. Hey, give someone else a chance to read it. Read it out. Jonathan Jenick? Oh, really? All right. Throw it in. All right, you get a jacket. And then for a hoodie. Reach in, grab one out for a hoodie.
Jamie Omohani.
Jamie Omohani? That's you? All right. That's a hoodie. We got 2 more to give away, and then we're done. 2 more jackets to give away. Reach in, grab one. Now it's it. Theater to go in. James Quick. James Quick. Anybody? Who? James Quick? Oh, no, okay. Here, just reach in, grab one out. Got 2 more of these to give away. Sharon? No Sharon?
I can give it to her. She left.
Now she got to be here. Okay. All right. But you can reach in for another one and tell her. Sorry.
Angad Singh.
Angad Singh? Okay, fill that in. All right, I'm going to grab this jacket in a second. Reach in for the last jacket.
Let's make propulsion. Dustin.
That's the one. That's the one? Wait a minute.
That's mine.
Is this your card? All right, you guys got a jacket. Thank you.